You have just joined session 7B, AI for Weather and Climate, Part 7. I'm Sue Haupt of the National Center for Atmospheric Research. I'll be chairing this session, and we have a wonderful series of speakers lined up to tell you about their most recent applications. First up is Sebastian Lerch of Potsdam Institute of Technology this morning. This noon, telling us about incorporating large-scale spatial information into ensemble post-processing via autoencoder neural networks. Sebastian, please share your screen and you're free to go.
Thanks, I hope you can hear me and see my screen. So I'll be talking about post-processing and in particular about our ideas for incorporating spatial information into neural network-based post-processing models. So I will start with something that probably most of you are aware of, that ensemble forecasts from numerical weather prediction models are great tools because they do provide probabilistic forecasts. However, they often show systematic errors such as biases or a lack of calibration, which means they require some sort of post-processing to provide useful forecast in practice. And this is typically achieved via statistical models. We call them distribution regression models for post-processing, which take the ensemble forecasts as input and produce a probability distribution as forecast output. So here you can see a simple example of some widely used models, the ensemble model output statistics, or EMOS approach in short. And this is graphically illustrated on the left. So the ensemble forecasts, in this case of temperature, are these blue bars. And these serve as the input for the statistical model. And the output is this green curve, so a probability distribution for the future temperature observation. For temperature, we can assume the forecast to take the form of a Gaussian distribution, meaning that we model the conditional distribution of temperature given the ensemble forecasts via a Gaussian distribution. And we can link the distribution parameters to the input to the ensemble forecasts of temperature. For example, we can specify the location parameter as a linear function of the ensemble mean, the standard deviation parameter as a linear function of the ensemble standard deviation, and by then fitting these coefficients A, B, C, and D, we can enable the model to correct these typical errors in the mean and the variance of the ensemble. So these models are now very widely used in research and operations. They often show good results, but they do have some limitations. For example, when it comes to incorporating additional predictors beyond just a temperature forecast, because one would then have to decide how to link the distribution parameters to all different kinds of input variables. And to address this, Jeff van Rasm and I have proposed a new semi-parametric approach that is based on neural networks. In particular, we propose to use a neural network that outputs the distribution parameters using inputs from the ensemble prediction system, which can be arbitrary predictors, for example. And these neural networks, they are designed to learn arbitrary nonlinear dependencies between predictors and the distribution parameters. They do so in an automated and data-driven way. And as I will demonstrate in the next slides, we also use some techniques to enable the model to be locally adaptive, even though it's learned for multiple locations in parallel. And if you want to find out more details about what we have proposed, you can take a look at our paper that has been published 2 years ago or so, or you can find all the code and data following this link to the GitHub page. So I will briefly introduce the neural network models for post-processing because this will then serve as the basis for extending these models to also incorporate spatial information later on. The data set that we use is a 10-year data set of forecasts and observations. Forecasts are 2-day-ahead forecasts of temperature and 17 other meteorological variables from the ECNWF. We have station observations over Germany at 500 locations. And we use the data from the last year as a test set, and we use 2 training sets, one using 1 year of data and one using all available years of data that we have. And what you can see here is a schematic sketch of the neural network models that we propose. So you can see as output, we obtain the distribution parameters, so of the Gaussian forecast distribution for temperature, so the mean and standard deviation parameter. And as inputs, we use the ensemble forecast of temperature. We calculate mean and standard deviation after interpolating the forecast to station locations. And we do that not only for temperature, but also for these 17 other meteorological variables, along with information about the station, such as coordinates or altitude of the station. We estimate a single neural network model jointly for all 500-something locations, but we make the model locally adaptive by using a technique called embeddings that does come from natural language processing, meaning that every station ID is mapped to a vector of latent features that are used as additional input features to the neural network, allowing the neural network to learn some local adaptive properties. The models are trained by minimizing the continuous rank probability score, or CRPS in short, which is a non-standard choice in the machine learning literature, but it's also a mathematically principled sort of custom loss function for this distribution regression task, because we want to have a probabilistic output distribution as our forecast. Now, to quickly give you an overview of the results, you can find more details in the paper. This again is showing the results in terms of the CRPS. So lower values indicate better forecasts, and there are two columns. One is just using 1 year of training data, and one is using the full 9 years of training data. The ensemble achieves a CRPS of 1.16, and using a local EMOS model, local meaning that we estimate a separate model at every location. EMOS was this simple statistical model just using the temperature forecast as inputs. We get an improvement of something like 20% in terms of the CRPS. And if we use state-of-the-art benchmark methods from statistics or machine learning, we get another maybe like 10% improvement in terms of CRPS. This is an EMOS model that has an extension via gradient boosting, and the second variant is a quantile random forest-based model for quantile regression. And the neural network models perform best among the comparisons. They outperform the state-of-the-art benchmark models by something like 3 or 4%. They also do work well on a local basis. So this again is a map of the 500 stations over Germany, and the stations are plotted in blue if the neural network model is best at that station, and in orange if one of the benchmark models performs better. And you can see that the neural network models are actually best at around 80% of the stations. So key advantages include that these models, as you can see, they provide more accurate predictions. They can learn nonlinear relations in an automated, data-driven fashion, but they also provide flexible starting points for extensions, and this is what I want to focus on today. They can be extended to other weather variables, such as wind gusts. There is a talk by Benedikt Schulz in one of the previous sessions today. They can also be extended to different types of output distributions, but today I want to focus on something else, which is incorporating additional sources of information, particularly incorporating spatial information into these sorts of models. And this is something that would not be possible in the simple statistical model frameworks, but is now possible if we use these sort of deep learning technologies. So to think about why this is important, we can recall how these forecasts are actually provided to us, because they do come as gridded forecast fields of forecasts of these weather variables from the physical model. What we did thus far is we just interpolated them to the station locations over Germany, even though we have forecasts, or we downloaded them as forecasts over Europe, so as like 81 by 81 pixel maps. But if we perform this interpolation step, this means that we will lose all sorts of large-scale spatial information that may be contained in these 2D fields. It's actually even worse, because we don't have just one 2D field that we get, because every single member provides a physically coherent 2D forecast field. And thus far, we have just also interpolated across this ensemble dimension by computing just the mean and the standard deviation. So again, there may be some possibly important information that might get lost in this interpolation step. And we have been thinking about ways to incorporate these sources of information into these types of post-processing models that we have been looking at. And one idea for doing this is to use autoencoder neural networks for dimensionality reduction. Autoencoder neural networks are specific types of neural network architectures that aim to learn a compact representation of the inputs in an unsupervised way. To do this, the network is trained to recreate its own inputs, but of course, in order to prevent the network from just outputting what has been input, it does so by creating a bottleneck that uses fewer hidden units than inputs. So one does learn a low-dimensional representation of the possibly high-dimensional inputs. Now, in the context of these neural network-based post-processing models, what we do is in the first step, we fit convolutional autoencoder neural network models to learn low-dimensional representations of these spatial input fields. For now, I will be showing results that are just for the temperature forecast fields. And these latent representations, they have dimensions of something like 8 or 10 in the following examples. And then in the second step, we can take these learned low-dimensional representations and we can just use those as an additional input to our post-processing model in order to allow the model to also learn from a summary of these spatial inputs. By the way, all of this is ongoing work with Kai Posterer, who is at the Heidelberg Institute for Theoretical Studies. To show some examples of these convolutional autoencoder reconstruction, I've here just plotted a couple of random examples from the test set. So in the top, you can see the original input fields, and in the bottom, you can see the reconstruction by the convolutional autoencoder that had a latent dimension of 8. So this is quite a drastic dimensionality reduction from 81 by 81 pixel to a latent dimension of just 8. But you can see that even though, of course, these reconstructions are not really perfect reconstructions of the input images, you can see that the general sort of features seem to be captured relatively well in all of these examples. Of course, the interesting question remains, like, if we now add this in the second step towards the neural network-based post-processing model, how does this improve the results? And you can see here again the table that I showed from before. And if we now compare this to a neural network that includes these autoencoder inputs, you can see that we again improve the results a little bit further from the neural network models. This in particular is the case if we have a longer training set available, and not that much of an improvement can be observed if we have just 1 year of training data available. And you can see that the step, again, is about of the same size as the step that we had taken from going from the state-of-the-art statistical and machine learning models for post-processing towards neural network-based models. So to summarize what I've told you over the past minutes is that in general, these neural network models, I think, are very interesting tools for post-processing because they enable flexible, automated, data-driven modeling of nonlinear relations. They perform better than state-of-the-art approaches, and they can probably be further improved by incorporating, for example, spatial information via these convolutional autoencoder approaches. Now, this is all sort of ongoing work. What we are looking at the moment, for example, is to include also spatial information from other variables beyond just temperature to see whether that further improves the results. Also, these convolutional autoencoders lead to some interesting design questions. For example, the question of how to best account for the actual ensemble dimension of the input, and to also compare this with CNN-based approaches that directly use the forecast fields as inputs to CNN-based post-processing models. But with this, thank you for your attention, and I'm happy to answer any questions.
Thank you, Sebastian. That was wonderful. And I do remind everyone to put your questions in channel 3, Weather and Climate, on the Slack channel. But I'll go ahead and start out. So you've added the spatial information. I'm not sure if I understand precisely how that's working. With this autoencoder, you're reducing dimensionality. Is this like a regime type approach, or is it really giving some local information?
Yeah, so we don't use any like physical representation of regimes or anything of that sort. We just use the input fields and learn a low dimensional representation of these input fields. But we haven't really looked at what these autoencoders have learned. So that would be interesting to try to relate this, for example, to physically motivated of notions of weather regimes, for example, to explore this latent spatial representation further. But for now, we are just using these autoencoders to try to learn some summary of the spatial structure, and then try to allow the network by using those as additional inputs to learn something from this. But what is learned physically is maybe a much harder question to assess and answer.
Yeah, and I think that's going to be interesting as you progress in your work. Another question, you use CRPS as part of your loss function. How do you find that really improves your solution very much?
Yes, I think that improves the solution, and I think that's also something that I think has been learned a lot from the statistical literature on post-processing, in that using the CRPS loss directly tailors your loss function to the task that you're performing, because you're comparing a distribution forecast and a real valued observation. If you would just use something like the mean squared error as a loss function, then you would not be evaluating any probabilistic aspects of your forecast. You could replace the CRPS by something like a log likelihood, so using like a logarithmic score that would probably lead to similar results. But if you just evaluate like point forecasts, then you would probably improve upon those.
Okay, we have another question. Could you elaborate on how you're using the embeddings?
Yeah, so the embeddings they just map every station ID to a vector of latent features, and we just chose a dimension of 2. And they are intended to make this model locally adaptive, because we just estimate a single neural network jointly for all 500 stations. But these embeddings then allow to additionally include some information about the station ID. And we have looked a bit in trying to understand what these embeddings maybe incorporate or maybe have learned. And it seems to be, at least in the more important dimension of those, something like a correction of the height of the station in relation to the height of the model grid point, for example. You can find more details on this in the paper by Stefan and myself, where we also look at, for example, what happens if you leave out these embeddings and how the results change, for example.
Okay, thanks so much, Sebastian. I think we need to move on. Our second speaker today is Charlie Becker of NCAR. He's going to be talking about evaluation of 2 machine learning approaches for the objective identification of convective storm mode using convection-allowing model output. So Charlie, take it away.
Okay, thanks so much, Sue. Hopefully you guys can see the screen here. Yeah, as Sue mentioned, we're talking about the evaluation of a couple of different approaches. One is a supervised approach and one is a semi-supervised approach for the objective identification of convective storm mode. This project is led by Ryan Sobash, David John Gagne, and Craig Schwartz. Okay, so some broad motivation here. Previous classification efforts have primarily used observed storms as opposed to CAM output, which we'll be using. This could be especially useful to forecasters, especially with the growing number of ensemble members, where the human interrogation of each individual ensemble member is incredibly time consuming and not always feasible. And of course, having a probabilistic model can increase forecast confidence. So the input data that we're going to be using is generated through WRF over the CONUS, and it's from fall of 2010 to spring of 2015. The storms within there are identified using the Hagelslag software suite developed by David John Gagne as an object-based algorithm. Once we identify where the storm is at, we center the storm and then just extract a patch of with an arbitrary kind of radius that's kind of a tunable parameter for us to extract just a full patch, and then we'll be using these patches as inputs into our model. On this particular case, the output data is 2,000 hand-labeled storms for the supervised model, that is, to begin with. And as you can see kind of on the right here, there's not always perfect agreement. This is a very subjective process as to what the convective mode actually is. And so when you get experts, there's not always perfect agreement. And this is an extremely time-consuming task and it requires the use of experts. It's not as simple as identifying, crowdsourcing the identification of cats and dogs, for example. And then we augmented these storms on, did some rotation to them to increase the total training data by a factor of approximately 10. With the supervised model, it's a fairly standardized approach here, where the input variables we use are composite reflectivity and updraft helicity. The labels, at the end are just 3 specific labels: supercells, quasi-linear convective systems, and disorganized systems. So next, I'll talk about this semi-supervised approach, which is a little bit more complex. As far as an input variables, with this one, we only used composite reflectivity, and it starts out as a similar approach to with a CNN as the supervised approach, However, instead of ultimately mapping to the hand labeled storms, we're going to map to a proxy output in this particular case. And the proxy task that we're mapping to here is just a binary value that we used the exceedance of updraft or the maximum updraft helicity of a storm. So in any given storm, if the maximum updraft helicity exceeds a certain value, map it as a 1 or mark it as a 1. If it's below that threshold, then mark it as a 0. But before that, importantly, we have this latent vector where we're bottlenecking all the information into this latent vector, flattening that vector out entirely. And that's ultimately the information that we care about. We don't end up using the actual, the proxy output in inference mode at all. So after we train it, we run inference on all the training data again. We extract all the information in this latent vector, and it's in this latent vector that we then perform some clustering on. And so we've chosen to use a Gaussian mixture model to perform the clustering on. And then once we have our clusters, we move on to the semi-supervised approach, which is really the humans taking a look at some of the sample storms with there and then assigning those storms a particular label. And so what that kind of looks like is something like this. So in this particular case, we have cluster 0, 1, and 2 from left to right. Cluster 0, might say in this particular case, okay, most of those storms have a linear kind of setup or linear feature. So let's label that as QLCS. The middle appears to be pretty disorganized, and the right likely to be supercellular in nature. I do want to point out that you don't just, even though we only have 3 labels, you can use more than 3 clusters. And in fact, we used 7 clusters in this particular case. And it's just when you go through and identify, you can get some better separation by using more clusters. And then when you go through and look at each individual cluster, you just have to label that cluster one of the 3 ultimate labels that you're interested in. So we took these 2 different models and we set it up in the spring experiments, the HWT experiment, and we ran in real time both HER forecasts and WRF forecasts, and then made predictions with both models, and then got some feedback from the HWT participants. You can see some survey results in the bottom right. And, the key takeaways are, that the CNN was subjectively rated higher than the semi-supervised GMM, though both did show some skill. The performance on the WRF data was marginally higher than the HER data. This isn't a big surprise because we trained on WRF data and not on HER data. And the biggest difference was the lack of consistency through time with the Gaussian mixture model. So regarding that last point, this is maybe kind of a small example of some of the inconsistencies of the GMM. You see the relative percentages of the type of predictions on the top of these cells through time. But I think just of note really is the fact that in the bottom one or in the top panels, you don't see a ton of, the structure doesn't seem to change all that much through time here, yet the GMM is kind of bouncing back before, calling this a linear system and a supercellular system. And so maybe it struggles with, a line of supercells versus an actual linear system or a bow echo or a squall line. But you can clearly see, I think in both the upper and lower panels, you see a little bit of jumping around with the GMM, and the CNN has proved to be more consistent thus far. So moving on to the actual, you get some more, call it quantitative evaluation. To begin with, the evaluation of this is very challenging because there's no ground truth whatsoever. However, we would expect to see some differences in the storm report distributions for different mode predictions, given that our models are accurate. And so the approach we took to do this was to compute a neighborhood probability for each convective mode on an 80-kilometer grid. And then we compare that to any, all the SPC storm reports that fall within that neighborhood probability. And we used a threshold in this particular plot for, 2%, which matches up with the SPC. And then once we have all those storms, we compute the actual conditional probability for each hazard and convective mode permutation. So we're looking for, what is the probability that we see a tornado given that we predicted a supercell, or that we see a wind report given that we predicted QLCS. And so, to walk you through these figures, I want to start with the top panel. The top is the CNN, bottom is the GMM, left is the WRF data, right is the HER data. But if we look at the top panel, specifically the top left one, we see exactly, I think, what we would hope to see. And what we really want to look at is the difference in the respected hazards. So the difference between the colors across the, or the same color across the different modes or the x-axis. And so in this particular case, we see that the conditional probabilities are higher for both tornado and hail, when given or when predicted a supercell as opposed to a QLCS or disorganized. And that makes sense. That's exactly what we're looking for. We also, in the blue there in the middle, we see that we have a substantially higher conditional probability of having a wind report, given that we've predicted a QLCS. Now, if we compare the left to the right panel on that top one, the WRF and the HER, there's very marginal differences, but I think it is consistent with what the observers in the HWT experiment reported, that you still see similar patterns between the two. However, the differences between the different conditional probabilities across mode, the magnitudes aren't quite as great. So there's a little less separation, it seems, with the HER data, but it's very marginal. On the bottom, I think I just want to point out with the GMM that we do have skill in the same in the with supercell and the conditional probabilities for tornado and hail given a supercell, which are significantly higher than the other modes, which is good. However, with the winds, that's where I think you see it struggle the most, where it's predicting more wind reports given, has a higher conditional probability when a supercell is present as opposed to a QLCS. And that's consistent, I think, again, with the HWT participants noting that it kind of bounces back and forth and maybe struggles kind of identifying between the two. So next, I just want to really quick kind of just examine some sensitivities of them. This is similar panel. Now we're just looking at three specific ones. Red's probability of tornado given supercell, probability of hail given supercell in green, and wind given QLCS. And instead of using all of the predictions that came within that 2% contour, we just want to filter them out by the actual probability of the model. And we see positive slopes across the board, which is good. So the probabilities of these models are meaningful, and we're getting higher conditional probabilities when the model is more confident that we're seeing a certain type of mode. We see steeper slopes with the CNN than the GMM, although still positive slopes. And the only other thing I'll point out is you see these really steep kind of slopes at the very end of the tails of the curves in the GMM, which I think might be reflective that the GMM is sometimes a little too confident and it doesn't have kind of an even distribution of predictions or probabilities. And lastly, I just want to point out the same when we want to examine now the sensitivity of the neighborhood probability. So instead of just looking at everything within a 2% contour, if we bend that into higher neighborhood probability contours, do we see a positive slope? And again, we definitely see positive slopes as the probabilities of those increase quite a bit. You do see a little bit of erratic behavior towards the end on some of these, and we suspect that's just due to just not having enough reports and having a low number of reports in a given area at a given time.
Okay, please be finishing up soon, Charlie. Yep,
you got it. So, moving forward, it's we want to improve the GMM specifically, and we could use object segmentation changes or ML changes, and we've got a variety of things to try that I won't go into detail with, but I do want to, we're going to make some changes and then evaluate that in next year's spring experiment in 2022. And so with that, I'm happy to take any questions. Thanks for your time.
Okay, thanks so much. We are starting to get questions in the Slack channel. First one, asking if you tried methods beyond the GMM, and I assume beyond the CNN as well. For example, some that can account for non-normal covariance structures.
I don't think I tried anything for non-normal covariance specifically. I'm trying we did try some different clustering approaches. early on, both hard and soft clustering approaches. But, initially before the spring experiment, we were evaluating on some a pretty small test set of data that we had, hand labeled stuff that we didn't use for training. And it was a rather small set, so we didn't have a great tool to evaluate it. So I think it's still something that's worth looking into. But we found, I think, good enough separation with the GMM and haven't fully tuned it in respect that we're going to continue down that path. But I do think some other clustering approaches, we tried t-SNE, we did try some t-SNE in kind of doing some other clustering, but did not see the same results, at least in our first attempts. So thank you for the thoughts and question.
Okay, very interesting, thanks. And you can continue to post your questions in Slack, and our speakers can answer them there as well. But right now, I think we need to move on to John Haynes of CIRA, a combination of Colorado State University and NOAA. And he'll be talking about low cloud detection in multi-layer scenes from GOES ABI using machine learning methods. John?
Okay, thank you. Can you see that?
Yep.
Okay. So yes, I won't repeat the title. I'd like to acknowledge all my co-authors, mostly from CIRA, also Andy Heidinger from NOAA NESDIS. So the motivation for this work is that most cloud information that we get from passive sensors like the ABI or VIIRs is really concentrated near the top of the topmost cloud layer. But we know that multi-layer clouds are important and common in the atmosphere. And knowing where low clouds are, especially when they're under cirrus, can be important for a number of applications, including aviation forecasting. So, given this VIS and IR satellite image, you might think I might ask you the question, what does the vertical profile of cloudiness look like at these locations? And if you ask that to an operational user, oftentimes what I find happens is that they will go to a model like the GFS and look at a relative humidity profile and say, well, it's saturated in this layer or this layer, so there's probably cloud there. So the question that we had is, can we obtain this kind of information more objectively? So satellite products can sometimes reveal or hint at where low clouds are under higher layers. So for example, in this animation I just showed, which is an RGB image, the low clouds are kind of highlighted in blue and there's cirrus on top of it in white. And as humans, we understand that just because there's cirrus doesn't mean that the low cloud underneath went away. It's still under there. So the question is, how can we determine that more objectively? There are some products designed to address vertical cloud structure in the atmosphere, and I just want to talk about one of them right now, and that's the cloud cover layers, or the CCL product. So CCL, in its operational form, classifies scenes into one of 6 categories, and this uses combinations of high, mid, and low cloud, HM and L. So you can see in this animation in the lower left, this is an example of the CCL product through the CONUS, and you can see that there's a cyclone going on there. So for example, the purple colors here are the HML category, so you have high, mid, and low together. But there's other places where, for example, you just have low cloud in orange here. And this is actually a very good product. It works very well for upper layers. But there are some problems with it when you start having multiple layers, and specifically in the low levels. So on the right here is sort of a bar graph that hints at this. Basically, low clouds are often missed by the CCL, and I'll talk more about the data set that went into this, but basically the orange is the CCL product, frequency of occurrence in these various categories, and the blue comes from a radar LiDAR data set, a spaceborne radar LiDAR. And what you can see is there's some compensation going on where the categories that include the L often are not represented properly by the CCL, and it tends to place those clouds in other categories. So our question is, can we use machine learning to predict the presence of low clouds in the atmosphere, given that traditional remote sensing methods have problems with this? So we approach this using 2 different types of models, random forests and artificial neural networks. All the algorithms I'm going to describe are trained using information from the GOES ABI, plus some cloud proxy information, which I'll also describe shortly. For the truth, we are using the 3-dimensional observed cloud structure from 2 research satellites, NASA's CloudSat, Cloud for profiling radar, which is a W-band radar, and the Calypso LiDAR. And so what we have is CloudSat or Calypso will fly over a scene, and whereas you get sort of the large scale picture from maybe the ABI, like you see at the bottom here, when CloudSat or Calypso flies over, you get this nice vertical profile of where clouds are located. So again, these are non-operational systems. So we can't do this in real time, but we can use this information in an a priori sense. So we've created a labeled joint radar/LiDAR/ABI data set to perform these evaluations for machine learning. And it consists of CloudSat and Calypso height and pressure resolved cloud boundaries matched to the GOES ABI data for a 9-month period from October 2018 through June of 2019. So it's about 22 million radar profiles, which we divided into a training and a testing data set. We did attempt to account for parallax, which is sort of shown in the diagram on the right. And we can do that because we know the actual heights of the clouds from the active sensors. Some limitations just to keep in mind are that the A-train has a constant local time of ascending node, which means that there's no real diurnal cycle in the data. CloudSat operates in daytime only anyway since 2011, so this is a daytime data set. And CloudSat does miss some boundary layer clouds just because of characteristics of the instrument. Although Calypso, which is also viewing basically the same space, will often pick up those clouds as long as there's not like a highly attenuating cirrus cloud or something overhead. So for algorithm training, the inputs that we used are shown in this table on the right. Basically, for the version I'm going to show you, we used all 16 ABI channels. We've also done this with using some common ratios and channel differences, and actually giving it all 16 channels performs best by a little bit in our experience. So in addition to that, we use relative humidity in the lowest layers, which is this RH max. This comes from the GFS. We have a separate study that shows that relative humidity does act as something of a load cloud proxy in certain circumstances. So we give this to the algorithm and let it decide whether it's going to use it. And there's also some surface information, including like snow and ice flags at the surface. And the truth in these cases is the matched CloudSat data. So we ask, was a cloud present in the lowest layer? This is a classification problem. And we define that as at pressures higher than 631 hectopascals for various historic reasons. So again, the models, we have a random forest model, and I'm just giving a couple of the parameters here. These results used 125 trees, and we cut it off at 30, a depth of 30. The neural network has 3 fully connected layers and between about 40 and 70 hidden units per layer. We use 5-fold cross-validation for both of these to sort of do this hyperparameter tuning. And we have a paper under review, so the full numbers are going to be in that paper. So now I'd just like to talk about model performance here. So I'm just going to concentrate on this these top lines here. These are statistics for low cloud detection on our testing data set for the entire data set. And on the left, you'll see the probability of detection of low cloud. In the middle is the false alarm ratio. And on the right is the CSI, which is kind of a mix between the two. And what you'll see is, so the orange bars are the original CCL algorithm, and the green is the neural network, the purple is the random forest. And you'll see that there's an increase in the detection ability of somewhere in about 10 to 15% range, and a significant decrease in the false alarms using the machine learning methods. And that's good, but where the real benefits seem to come in are in cases where the ABI thought it was looking at cirrus. It had classified the clouds as either cirrus or this overlapping category, which is basically where it says, I think there's multiple layers, but I'm not quite sure where those layers are. And so in those cases, you can see that the detection with either of the machine learning method goes way up for low clouds underneath cirrus, or in these overlapping case, with a slight increase in false alarm to go along with that. But if you look at the CSI, this is still quite a large increase in the utility for low cloud detection in those cases. Again, the neural network and the RF are very similar actually in their performance, and I'll show you that geographically too. So again, this is the probability of detection, false alarm ratio, and CSI for each of our methods, and then the original algorithm. And this is where you can see that geographically, these results, when you average geographically, it kind of washes out, but there are pretty big increases in the detection ability with either of these methods over the higher latitudes, especially. Right, but again, you can see that I should have mentioned this earlier. These are pixel, but this is pixel by pixel, so we're not using the surrounding cloud scene at the moment. But even on a pixel by pixel basis for the results, you can see how very close these are. We're thinking about why that is. What can we learn from that? What are these algorithms learning exactly? I'm going to skip this in the interest of time, but just to show you on this right side, here's a full disk image of the CCL product before machine learning. And in the lower right is after we supplement the CCL product with the low clouds that we detect using the random forest. And you can see that there's a lot more of these deep purples in places that we'd expect them, like in the mid-latitude cyclones and in the fronts and here in the tropical convection. So it's supplementing low cloud. And you will see we've introduced some of the higher over low category, which wasn't possible before. And that's some of these pink colors that you see scattered around. I just want to talk briefly about feature importance here. So we looked for the random forest at permutation-based feature importance, which is one of the two common ways to do it for a random forest. And this one probably makes the most sense in this case. So what you're seeing on the left here is a ranking of which of the features were most important for the determination on the testing in the entire testing data set. You'll notice first that the visible channels appear near the top. There's only one infrared actually before the rest of the infrared come in here at the bottom. But the top three channels kind of make sense to us. For example, you might imagine a situation where you have a cirrus cloud alone, which would produce a significant reflectance in both the 0.47 and 1.37 band. But if you place a low cloud underneath that, the reflectance might go even higher at 0.47, but you're not going to see it in much as in 1.37 because it's in a water vapor absorption band. So, you know, it kind of makes sense. In fact, we fooled around with this ratio of the first to the third as one of our inputs. That was one of the first things we thought of before we actually just threw everything at it. The max relative humidity also turns out to be important. The feature dropout, just very briefly, it speaks to how important are these features. So what it shows is, it shows the algorithm performance in terms of the CSI score on the testing data if we drop n of the bottom least important features at one time. So for example, if I drop these bottom 5 features, then that's the CSI score. And you can see that we can drop like 10 features before the performance of the algorithm really drops off. So to me, that tells us that we have a lot of correlation between the channels, and it suggests a simplified model will perform just as well. And in fact, that's what we're doing as we transition this to more of an operational sense. So just very briefly here, what are we doing now? Well, we can run this at nighttime. Just in other words, just using the infrared channels. The performance decreases, but it's still an improvement over the original algorithm. We're trying to translate this to other sensors like VIIRS. We don't have a good CloudSat Calypso VIIRS data set to do these matchups. There are some periods where they overlap, but it's not a large data set. However, we want to use sort of transfer learning to do this. How can we utilize the ABI channels and try to transform them into what VIIRS would see at those wavelengths? And finally, we've tried to do this at other vertical levels. So this is kind of new work, but we're using multi-output prediction with the RF model to try to determine the cloud structure in each of 5 levels. And these 5 levels have been determined by our partners at AWC that we're working with. And just to say very briefly that this is quite promising, and we can actually reproduce the cross correlation between layers pretty well when we do this, but this will be a talk for a different time. So my summary follows. This table sort of summarizes our results. I will just say that we are implementing now in the Cirrus slider interface, which is publicly available. And our future work, again, is to retrieve multiple levels. And we want to move beyond pixel by pixel determination, for example, going to something like a CNN and seeing how that performs. Thank you.
Okay, thank you so much, John. This is fascinating. So you are running it quasi-operationally now, I take it. And what is the latency? How soon are you able to diagnose?
We haven't actually got it running operation into the CCL algorithm. We do run the CCL operationally, What we're doing right now is we're implementing the random forest implementation as kind of a post-processing routine. And that can run in just a few minutes, actually. So if that, and we haven't tried it, if you use a lot of processors at once, we think we can get it down to a very short amount of time. So it doesn't really add a whole lot to the processing timeline. But it will be in Slider once we finish that implementation, but it's not right now.
Okay, very impressive results, being able to see clouds below. I think we're going to need to move on to the next speaker, who is Jonathan Frame, talking about data-driven streamflow simulations of extreme high-flow events. And Jonathan is with NOAA.
Okay, I believe I'm sharing my screen, is that correct?
Correct. Not in.
All right.
Looks great.
All right, thank you very much. So yeah, I'm going to be talking about deep learning for streamflow predictions of extreme events. And these days, there's no need to really motivate the need to simulate extreme runoff events. But as we saw last month, the Hurricane Ida left a huge impact across a lot of the United States, all the way from the Gulf to the Northeast. So extreme event prediction is extremely relevant today, and it will most likely be important well into the future. So the motivation for this project is seeing how deep learning can make predictions of extreme events. And historically, there's been a little bit of a criticism of deep learning for extreme events. And a lot of this criticism came from some studies that were done early on in the research of neural networks in hydrology. And they were using small samples on a limited number of catchments. And they were doing experiments comparing machine learning models and traditional conceptual and process-based models. And they found that neural networks have difficulty forecasting large magnitude events if those magnitudes were not included in the training period. And that led to some criticism of neural networks as black box type models that if they can't really simulate the processes that are happening in the hydrologic regime, then they might not be able to be trusted when making predictions of larger extreme events. But these studies were done early on in the research, and so they were done with limited data and small numbers of catchments. These days, we've expanded our research to doing, we've expanded the training of neural networks to include many catchments and with a lot more data. But even still, there's been a push to solve the problem of using deep learning for predicting extreme events through theory-guided machine learning, with the thinking being that if you have physical constraints in your deep learning prediction, or a combination of a processor conceptual model with a deep learning model, then the hydrological processes that are represented in the conceptualization will improve the prediction in extrapolated conditions. And there's been a couple of, actually there's a number of studies that are now comparing what's referred to sometimes as theory-guided machine learning, or knowledge-guided machine learning, or hybrid modeling. And a lot of the results show that the hybrid modeling or the theory-guided machine learning is doing very well. But from what I've seen, it's kind of not quite clear that the theory-guided or knowledge-guided machine learning is actually outperforming the pure data-driven models themselves. And so the motivation of this study was to kind of revisit the idea of extrapolating deep learning models into extreme events, to see if the theory-guided machine learning is still necessary. And so for this study, we used two different models. One is a pure data-driven model, we used two data-driven models. One is pure data-driven. On the left is just a standard long short-term memory model. And on the right is a mass-conserving long short-term memory model. So the model shown on the right here is a theory-guided machine learning model that is able to conserve mass. So if you have an input that is a mass input like precipitation into a hydrology model, the amount of mass that goes into the model should be the same amount of mass that goes out of the model, and that is constrained through the model architecture. So that's a hard constraint on the model architecture. Now, how do we define an extreme event? So I used the USGS Bulletin 17 to define what an extreme event is. And so the idea here is we fit a probability distribution to the annual peak flows on each basin, and that probability distribution is a log Pearson type 3. And so for every catchment in this study, we fit a log Pearson 3 distribution according to the Bulletin 17 guidelines, and then we are able to split the to characterize each individual year by its peak flow return period. And so what that looks like is on the left here is a kind of a spaghetti plot with 500 curves, and those curves show the return period versus the annual peak flow at 500 basins that were used in this study. And so you can see that flow goes up and return period goes up, but the curves don't necessarily look identical. And so there's a lot of diversity in the return period curves. And this is actually a big strength of modern deep learning models, that they can be trained on many basins that have a diversity of flow conditions. And so using the return period to identify the extreme events, it's a single hydrologically universal statistic that maintains basin diversity and allows for a sufficient number of test cases. And so for this experiment, we trained the model on return period years that were 5 or less. So those would be high probability years where the peak flow is likely to be exceeded in less than 5 years. And we left out of the train period for testing any year that includes a return period that is greater than 5 years. And so this allows us to train on high probability events, and then we are testing on low probability events. So we are testing the ability of a model to learn hydrologic responses on high probability events and train and to then test that response on a low probability event. So an extreme low probability event, so a high flow event. And so here are the results. This is a box and whisker plot that shows the results of the absolute percent error of peak flow. So this is a metric that is calculated only on the peak flow of the simulated hydrograph and the observed hydrograph. So we just take the single largest flow value that was simulated and the single largest flow value that was observed. And this is an important characteristic in extreme events because the extent of flooding is often driven by the highest flow of the hydrograph. And so each one of these colors represents one of our different models. So we have the LSTM in blue, that's the pure data-driven model. We have the MC LSTM in orange, that is the theory-guided data-driven model. We have the Sacramento soil moisture accounting model in green, that is the conceptual model, and then we have the national water model in gray. Now the reason that the national water model is dashed in gray is because we weren't able to recalibrate the national water model, but we did calibrate SAXMA on the same high probability years that the LSTM, the MC LSTM were trained. So there's a direct comparison between the blue, orange, and green results, but not a direct comparison with the gray results. And then this dashed line in in the plot splits the in-sample data that was used for training from the out-of-sample data that was not included in the training set. And each one of these values here, the n values, represents one single year for each. So I refer to it as a basin year. So there's 500 basins, and each year that has a peak flow is included in these. So on the left, we have in the training period, there is almost 6,000 basin years, and on the right are the out-of-sample years. So we have not as many samples in the training period, but we have a sufficient number of samples to draw conclusions. And so we can see that the LSTM model without a mass conserving constraint has actually the best average performing model. The mass conserving LSTM also performs better than the conceptual model. In some instances, the national water model actually does perform better on average in the out of sample conditions, but remember that the national water model was calibrated using all flow events. So we weren't able to calibrate the national water model, leaving out the high flow events. So this is just the peak, the absolute percent error of peak flow. We also did the analysis on the standard time series metric. And so we split the years up by their peak flow return period, but we calculated the metrics across the full water year. And the results still hold with the standard metrics of mass cycle efficiency and the correlation coefficients and the biases and the standard performance metrics. But these, of course, were calculated across the whole year, not necessarily on the peak events themselves. And so I was surprised because I thought that the mass conserving LSTM would actually do better in extreme events because it wouldn't be able to eliminate mass from the system like the LSTM possibly could do. So in thinking about that, it occurred to me that Keith Bevan had proposed a hypothesis that mass conservation actually wouldn't be beneficial for deep learning because there are mass bias errors in the training data. And so Keith Bevan proposed a hypothesis that the reason that deep learning models do better than conceptual and process-based model is because they are able to compensate for mass bias errors in the training data. And here are some results that show that that is absolutely true. This is the total mass bias of the conceptual Sacramento model with two sets of forcings. One is DAMET forcings, one is NLDAS forcings. And you can see clearly that there is a huge mass bias error in the forcing data from DAMET and not so much in NLDAS. And if we look at the mass conserving LSTM, the results of the mass conserving LSTM shows that it does in fact compensate for that mass bias in the input data. And whereas the Sacramento model, the conceptual model, is not able to compensate for that mass bias error, the theory-guided deep learning model is able to compensate for that mass bias error. So while the theory-guided deep learning model doesn't necessarily give better performance during extreme events, it is still able to compensate for mass bias errors in the input data. And so that's everything. Thank you very much. And I'm at the U.S. National Water Center and at the University of Alabama. And this work is part of a paper that we just submitted to HES. So thank you very much.
Okay, thanks so much, Jonathan. Really applicable problem, and glad to see that you've made such headway. So, you know, your conclusions are showing that having some theory guidance does really help. Do you see us getting to a place where we will no longer need that and we can use just data if we have lots of it?
I think there's definitely a place for theory-guided machine learning. I think there's definitely a place for process-based models and conceptual models. I think the most important thing is knowing when to use what kind of model.
Mhm. And okay, so you opened that up. When do you need the theory?
For instance, if you have an input and an output that your model will represent, but in between there are some variables that are perhaps unobservable. For instance, in the hydrology sense, some soil moisture condition or ice condition that isn't, we don't have data to train on at this point. So if there's a variable that isn't necessarily included in an observation set that you can train on, the process-based model, we can have confidence that a process-based model gives us the right answer because it does well predicting the output.
Mm-hmm. Great, well, thank you. And I suppose it adds some element of explainability too, which has been a big theme at this conference.
Absolutely.
Okay, well, thank you. I think we'll move on to the last, but certainly not least speaker, and that is Yingkai Sha of University of British Columbia, talking about a hybrid analog-ensemble convolutional neural network method for post-processing precipitation forecasts. Sounds fascinating, Kyle.
Thank you. Yeah, so the topic is precip forecast post-processing, and the researchers collaborated with Dr. Yingkai Sha from the National Center for Atmospheric Research, Dr. Greg West from Bissell Hydro, and Professor Alan Stahl from UBC. So we know that precipitation forecasts are important in hydrological applications, but they can be biased and unreliable because of imperfect initialization parameterizations. So then post-processing should be applied to improve the quality of precipitation forecast. And it is especially important in British Columbia because the province rely heavily on the operation of hydroelectric facilities. And then also motivated by the importance and potential benefits, this research aimed to post-process precipitation ensemble forecast produce bias-corrected, probabilistically calibrated, and physically realistic precipitation spatial temporal sequences. So here we're working with the global ensemble forecast system, the GEFS, zero UTC daily initializations, 3-hourly forecast lead time from day 0 to the end of day 6. And our target variable is a quarter degree total precipitation with original subset centered around British Columbia, Canada. And here our forecast post-processing models take uncalibrated forecasts as inputs and produce post-process products with 3 methods being applied in sequential order, and they are the analog ensemble, minimum divergence, Schottky shuffle, and convolutional neural networks. All the methods need to be trained, and here 3 training datasets are applied. Firstly, the GFS3 forecast version 12. This data is available in the past 20 years and produced by the same configuration as its operational counterparts. We use it as training inputs, and we also use it to conduct post-processing experiments, which the performance of our methods can be evaluated. And then the ECMWF analysis version 5 or the ERE5 is used as training targets. We use it because it covers the availability of the GFS3 forecasts, so they can be paired, and it has consistently good quality in our region of interest. And then the ETOPA1 gridded elevation is used to provide as an additional predictor. So here our research domain covers British Columbia and Southeast Alaska, and the verification data is based on the BC Hydro Station observations. So there are 84 of them located in 3 hydrologic regions, and the observations are independent to the ERE5 data simulation. We use it for forecast verification only. They're not involved in the training process. And here verification time period is from 2017 to the end of 2019, 3 years in total. So here we begin to introduce our methodologies. Firstly, the analog ensemble. So this method takes the ensemble mean of raw forecasts as inputs and produce calibrated members per location per forecast lead time. So here, when today's forecast is issued, the analog ensemble would take it as prediction inputs and then identifies nearest neighbors based on a similarity search within the reforecast training inputs, and then collect the ERE5 training targets to form the calibration outputs. Generally, this is a specific example of k-nearest neighbor regression, and the distance measure for similarity search is a linear combination of precipitation and precipitable water, both half millimeter per time units. As a minimal divergence shuffle, so this method takes the analog ensemble members as inputs and convert them into spatial temporal sequences that are physically realistic. So accumulated precipitation can be estimated along forecast lead times. So technically, this method is not hard to implement. So given the ERA5 as training data, this method identifies the sorted positions of the sorted ERA5 and then use these positions to re-index sorted analog ensemble members. So they become spatial temporal sequences. Physically, what does it mean is that given analog ensemble members being calibrated on individual forecast lead times, these are exchangeable members, so we do not know how they can be connected along forecast lead time. So what we do is we identify ERE5, which is already physically realistic. We use them as sequences and then identify their rank structures and use exactly the same rank structure to reorder the analog ensemble members. So then we can connect them. And here, this is minimal divergence Shaki shuffle is because the ERA5 is not selected by random. It's selected to minimize the distribution divergence between analog ensemble members in itself. And the last part of methodology, convolutional neural networks. So the output of the previous two algorithms can produce spatial temporal sequences, but we found it's still suboptimal and it contains small scale noise or unsystematic errors. And here CNNs are applied to reduce the impact of this noise. So our CNN takes three inputs. One is the output of the previous two algorithms, and then there are two extra predictors. One is the precipitation monthly climatology estimated from the ERA5, and there are also graded elevation. As in the CNN output would be a denoised version of the precipitation fields, which is expected to be more skillful. And here briefly about CNNs. So there are deep learning models that consist of trainable spatial operations, and they can handle graded information effectively, can capture nonlinear signals. And specifically, this research we use a unit-based architecture. As then moving on to the post-processing experiments. So given GFS reforecast in the testing period from 2017 to the end of 2019, it will be processed by the analog ensemble first, which produce two sets of ensemble members. One follows the conventional implementation, and the other one incorporates supplemental locations, which is a data augmentation technique. And then these two sets of members will be processed by minimal divergence Shaki shuffle, which brings two sets of results into with H15. They are the control part of the experiment. And then the CNN will be applied, producing two sets of our results ending with CNN. And then the H15 minus CNN would measure the benefits of our contribution, and SL minus no SL would identify the benefits of this data augmentation technique in our region of interest. And besides, we have quantile mapping as a non-analog ensemble control, which provides a bottom line of verification performance. Here we move on to the results, and here an example case is provided first. So here panel A is an example of analog ensemble member on February the 1st with 15 hours forecast lead time. As if we compare it with the ERA5 on the forecasted time, we see that the analog ensemble member generally captured precipitation along the coast and in the interior part of the domain. However, it's not physically realistic because pattern information is not available. And it is because analog ensemble is a univariate method which has to be applied on grid points individually. And then this is why we have minimal divergence Shaki shuffle, which takes analog ensemble members like panel A as inputs and produce It's output that has better spatial temporal dependencies. But here we think it is still suboptimal because of small scale noise. And a good way to characterize it is the ISO line of precipitation intensity here, 8.5 millimeter per day, which is roughly 90th percentile in February in this area. And we can see that it does not follow the extent of terrain and has small perturbations compared to the Area 5. And it's not just a visual problem only. If we compare station observations with grid point values, panel C actually releases relatively high precipitation bias. And then we have panel D, which is the output of CNN, which take panel C together with climatology and elevation as inputs. And here we see that its precipitation pattern is better organized, and its precipitation bias when compared to observations are also reduced, which also reflects the reduction of mean absolute error. So overall, in this example, our master produced more skillful precipitation forecast. We also did a set of systematic verifications, and here's a result of continuous ranked probability skill scores. So higher means better. And here all the lines are averaged from all stations. And the first two columns are results from August to March, which is the winter time. And then the second two columns are results from April to September, so summertime. And here, firstly, we see that all the skill scores are decreasing with increasing forecast lead time, but they are at least positive, which means they are better than a climatology reference. And here for the summer results, we see relatively large diurnal cycle with lower skill scores around 0 UTC or late afternoon local time. This is likely because of convective events in summer, which is harder to forecast and harder to post-process. And here, panel from E to H are a difference between ours and the control part where the CNN is not applied. And here we see positive skill score, which means the performance increase. And we found this increase is almost consistent with the increase of forecast lead times, except the impact of diurnal cycle in the summer. So relatively for longer forecast lead time and poor forecast, our masters can contribute relatively more. And then for panel I to L, where the supplemental location-based result is compared to the one that does not apply supplemental location, we see that it is also beneficial, but within short forecast lead times only, and its effectiveness decreases in longer forecast lead times, both in winter and in summer. We also did classification verifications with seriality heavy precipitation forecast. And here, heavy precipitation forecast is events is defined based on monthly 90th percentile. And with it, we evaluated in different regions, and here is a result in the interior parts of the domain. So firstly, looking at the reliability diagrams, with ours represented by dashed lines and the control part of experiments by solid lines, we see that ours aligned with the diagonal line better, which means it is more reliable compared to the control parts. And also by calculating the bias score here, lower means better, and there's decompositions of reliability, lower means better, and resolution, higher means better. We see that ours is also generally better than the control part of experiments in both day 1, day 3, and day 5. And we also measure the difference between the one with supplemental location and the one without. And we see that the supplemental location or data augmentation contribute relatively high in the resolution, which means the forecast can now separate conditional and unconditional events better. And actually, we did similar verifications in other regions, including the coastal and the subarctic watersheds, and we found similar conclusions of CNN can contribute to the forecast post-processing, and the supplemental location could also contribute, especially in the resolution part. And now we move on to conclusions. So we propose a novel post-processing method by combining 3 methods, the analog-ensemble, Shaki shuffle, and convolutional-neural networks. And here, this hybrid is verified well in British Columbia. It produced more skillful post-process forecasts overall by the CRPS results, and it's better than the analog-ensemble benchmark for calibrating heavy precipitation events based on bias score in these decompositions. And here, the hybrid is the first attempt that combines conventionally used requires post-processing with neural networks. And once it is operationalized, it will support hydrological applications in VII with good spatial and temporal resolutions. And in the end, I didn't mention neural network technical details, but there's a package available online where different unit architectures can be explored. And this work is based on this package. And thank you.
Okay, thank you, Kyle. Lots of interesting methods put together there. Have you tried using the convolutional net without doing the analog ensemble and Shocky Shuffle first?
It is theoretically possible, but in my early attempts, I find it's computationally heavy because we have multiple ensemble members. All of them are gridded fields across a large area. And also there are 5 dimensions of long forecast lead time, variable, and initialization time. So I think it does require more resources, and operationally it seems unpreferred.
Okay, so you're thinking then that sequence actually simplifies the type of data that you're passing to the convolutional neural net then to make it more successful. Am I understanding that correctly?
Yes, using neural networks only could be an interesting avenue to explore, but requires more computation.
Okay, thank you. So we're out of time for this session right now, but I do invite you to continue to ask questions of any of our speakers in Slack channel 3, and they'll be able to answer you on that Slack channel and continue the conversation beyond this particular session. So thank you so much for attending. I do want to point out that there is a plenary session coming up at 1:30 on AI and ocean science. And Christina, do you have any other announcements you wish to make?
No other announcements on my end. Hope to see you all at the plenary.
Okay, great. Thank you for attending.